1995 they presented early investigations on stacked memory in processors. 63. In the early 2000s, a team of Fraunhofer and Infineon Munich researchers investigated 3D TSV technologies with particular focus on die-to-substrate stacking within the German/Austrian EUREKA project VSI and initiated the European Integrating Project E-Cubes as a first European 3D technology platform, and eBrains with AO, Infineon, Siemens, EPFL, IMEC and Tyndall, where heterogeneous 3D integrated system demonstrators were fabricated and evaluated. A particular focus of the eBrains project was the development of novel low-temperature processes for highly reliable 3D integrated sensor systems. 64, United States, 1999-2012. Copper-to-copper wafer bonding, also called CU-CU connections or CU-CU wafer bonding, was developed at MIT by a research team consisting of Andy Fan, Adnan Rahman and Raphael Reif in 1999. 11. 65. Reif and Fan further investigated CU-CU wafer bonding with other MIT researchers including Qian Chin, Shamik Das, Chuan Seng Tan and Nisha Checker during 2001-2002. 11. In 2003, DARPA and the Microelectronics Center of North Carolina, MCNC, began funding R&D on 3D IC technology. 42. In 2004, Tesaran Semiconductor, 66, built working 3D devices from 6 different designs. 67. The chips were built in 2 layers with via first tungsten TSVs for vertical interconnection. 2 wafers were stacked face-to-face and bonded with a copper process. The top wafer was thinned and the 2-wafer stack was then diced into chips. The first chip tested was a simple memory register, but the most notable of the set was an 8051 processor forward/memory stack, 68, that exhibited much higher speed and lower power consumption than an analogous 2D assembly. In 2004, Intel presented a 3D version of the Pentium 4 CPU. 69. The chip was manufactured with 2 disks using face-to-face stacking, which allowed a dense via structure. Backside TSVs are used for I forward/O and power supply. For the 3D floor plan, designers manually arranged functional blocks in each die aiming for power reduction and performance improvement. Splitting large and high power blocks and careful rearrangement allowed to limit thermal hotspots. The 3D design provides 15% performance improvement, due to eliminated pipeline stages, and 15% power saving, due to eliminated repeaters and reduced wiring, compared to the 2D Pentium 4. The Triflops research chip introduced in 2007 by Intel is an experimental 80-core design with stacked memory. Due to the high demand for memory bandwidth, a traditional I forward/O approach would consume 10 to 25 W. 29. To improve upon that, Intel designers implemented a TSV-based memory bus. Each core is connected to one memory tile in the SRAM die with a link that provides 12 GB forward/S bandwidth, resulting in a total bandwidth of 1 TB forward/S while consuming only 2.2 W. An academic implementation of a 3D processor was presented in 2008 at the University of Rochester by Professor Abby Friedman and his students. The chip runs at a 1.4 GHz and it was designed for optimized vertical processing between the stacked chips, which gives the 3D processor abilities that the traditional one-layered chip could not reach. 70. One challenge in manufacturing of the 3-dimensional chip was to make all of the layers work in harmony without any obstacles that would interfere with a piece of information traveling from one layer to another. 71. In ISC 2012, 2 3D IC-based multi-core designs using Global Foundries 130 nm process Antizaraan's FA stack technology were presented and demonstrated. 3D maps, 72, a 64 custom core implementation with 2 logic die stack, was demonstrated by researchers from the School of Electrical and Computer Engineering at Georgia Institute of Technology. Circuit-3D, 73, near-threshold design based on ARM Cortex-M3 cores, was from the Department of Electrical Engineering and Computer Science at University of Michigan. Commercial 3D ICS, 2004 present. Sony's PlayStation Portable, PSP, handheld game console, released in 2004, is the earliest commercial product to use a 3D IC, an EDRA memory chip manufactured by Toshiba in a 3D system in package. The earliest known commercial use of a 3D IC chip was in Sony's PlayStation Portable, PSP, handheld game console, released in 2004. The PSP hardware includes EDRAM, embedded DRAM, memory manufactured by Toshiba in a 3D system in package chip with 2 dies stacked vertically. 6. Toshiba called it semi-embedded DRAM at the time, before later calling it a stacked chip-on-chip, COSI, solution. 6. 74. In April 2007, Toshiba commercialized an 8-layer 3D IC, the 16 GB THCM embedded NAND flash memory chip, which was manufactured with 8 stacked 2 GB NAND flash chips. 75. In September 2007, Hynix introduced 24-layer 3D IC technology with a 16 GB flash memory chip that was manufactured with 24 stacked NAND flash chips using a wafer bonding process. 76. Toshiba also used an 8-layer 3D IC for their 32 GB THGBM flash chip in 2008. 77. In 2010, Toshiba used a 16-layer 3D IC for their 128 GB THGBM2 flash chip, which was manufactured with 16 stacked 8 GB chips. 78. In the 2010s, 3D ICs came into widespread commercial use in the form of multi-chip package and package-on-package solutions for NAND flash memory in mobile devices. 6. Elpida Memory developed the first 8 GB DRAM chip, stacked with 4 DDR3's DRAM dies, in September 2009, and released it in June 2011. 79. TSMC announced plans for 3D IC production with TSV technology in January 2010. 79. In 2011, SK Hynix introduced 16 GB DDR3's DRAM, 40 nm class, using TSV technology. 80. Samsung Electronics introduced 3D stacked 32 GB DDR3, 30 nm class, based on TSV in September, and then Samsung and Micron Technology announced TSV-based Hybrid Memory Cube, HMC technology in October. 79. Cut through a graphics card that uses high bandwidth memory, HBM, based on through-silicon via TSV, 3D IC technology. High bandwidth memory, HBM, developed by Samsung, AMD and SK Hynix, uses stacked chips and TSVs. The first HB memory chip was manufactured by SK Hynix in 2013. 80. In January 2016, Samsung Electronics announced early mass production of HBM2, at up to 8 GB per stack. 81. 82. In 2017, Samsung Electronics combined 3D IC stacking with its 3D VNAND technology, based on charge trap flash technology, manufacturing its 512 GB Clough-Gate R1M flash memory chip with 8 stacked 64-layer VNAND chips. 83. In 2019, Samsung produced a 1 TB flash chip with 16 stacked VNAND dies. 84. 85. As of 2018, Intel is considering the use of 3D ICs to improve performance. 86. As of 2022, 232-layer NAND, i.e. memory device, chips are made by Micron. 87. Previously in April 2019 were making 96-layer chips, and Toshiba made 96-layer devices in 2018. See also Charge Trap Flash, CTF, FinFET, 3D transistor, MOSFET, Multigate device, MUGFET, VNAND, 3D NAND. Notes. Semi.org, PDF.
Yes, let's stop. The video is 52 minutes, and of course I not understand much of this. That's too complicated, but that's kind of this technology. The Intel going to make the future CPUs with many thousands of billions transistors. Some kind of 3D technology to build the transistors in multi-layers, silicon wafers in many layers with transistors in kind of 3Ds. But today they are just few millions. They are less like 10 billion, so they're going to do from like 10 billions to many thousands of billions and trillions in a few years, 7 years. I not really believe that, because that take many years to build this kind of factories. You have to start in like 2 or 3 years. They have to get started in 2 or 3 years to build this factories building 10,000 billions chips, yes, 10 trillions. No, Intel that did pronounce that they like to make the future CPUs for PC computers with like 10 trillions. 10 trillions is 10,000 billions. 10,000 billions transistors in just 7 years. 2013. We are 2023 next year in 2 weeks. So they don't have much time, because it will take many years to build this kind of semiconductor factories, and cost like more than 20 billions of dollars just to build it. 20 or 30 billions of dollars. They have to start like 4 years, like year 2026. They have to start building in 3 years. But they maybe do that. But let's read the next one. The next one is a short one. Let's read the International Technology Roadmap for Semiconductors.